These are the notes for AP Calculus on the topics of advanced area and volume problems. So recall, we already looked at the area between two curves using a vertical representative rectangle, like this, where the width is dx. You just take f of x is above g of x, the function that's on top, minus the function that's on the bottom, integrate from where the region starts to where it stops, all in terms of x. However, sometimes it might be advantageous to actually use a horizontal rectangle, in which case the width would not be dx, it'd be dy. And if that's the case, then you want to subtract, everything's going to be in terms of y. So you take f of y minus g of y, where f of y is the function further to the right, because that is a bigger x part. And then a and b are now the y coordinates, where the region starts and stops, instead of being the x coordinates. So then the whole integral is in terms of y. And we'll see how that sometimes makes things a little bit easier to work with. So on this first example here, it says let R be the region in the first quadrant bounded by y equals the square root of x minus 1. You can see is this graph right here. Sorry, there's not really a gap there. It's right there. And y equals 7 minus x. You see is that graph right there? As shown in the figure below. So it's in the first quadrant bounded by these two. Right there. And then we're asked to write an integral in terms of x and an integral or integrals in terms of y that gives the area of R, and choose one of these to evaluate to find the area of R. So let's start with what we're used to here. Well, first we need to find points of intersection. So to find this point of intersection, if it's not given to you already, you can just set the functions equal to each other. Square root of x minus 1 equals 7 minus x. And then to solve this, you can just square both sides. So give you x minus 1 equals, when you square that out, 7 squared is 49. It's like 7 minus x times another 7 minus x. And then you have a negative 7x and another negative 7x would be negative 14x. And negative x squared and negative x squared. Sorry, negative x and negative x would give you positive x squared. Then subtract the x, add the 1. 0 equals x squared minus 15x plus 50. And factors of 50 that have to be negative 15 would be 5, negative 5, and negative 10. So you can see it looks like we've got two different x coordinates, but we only see one point of intersection. So it looks like based on that we get x equals 5, x equals 10. However, there's only one point of intersection based on this. So to see which one would logically make sense, just let's go ahead and find these points here. Well, to see where this one equals 0, you can see when x equals 1, so this is the point 1, 0. And if you set this one equal to 0, you can see x would have to be 7, so this is the point 7, 0. So it has to be between 1 and 7, so this one, x coordinate would have to be 5. And then the y coordinate then, to find that you can substitute 5 into either one. If you substitute 5 into this one, it would be 5 minus 1 is 4, square root of 4 is 2. Or here, substitute 5, 7 minus 5 is 2. So it's the point 5, 2. Now the reason why we're getting 10 as an answer also, is because when you square this square root, it actually turns into an entire parabola. So if we were to draw the entire parabola like that, and then extend this line here, it would actually intersect at another x coordinate of 10 something. But in this case, that's outside of the first quadrant, and this is the square root of x minus 1 graph, not the entire parabola, so it's only half the parabola. So that's why this one doesn't apply, but that's why we're getting that answer. Alright, so now we're all set up. We found all those points there, x and y coordinates, to figure out our integrals. Let's start with the one you're more used to here with using a vertical rectangle. Well, you can see if you draw the vertical rectangle right here, it's between square root of x minus 1 and 0, y equals 0. But notice that's not always the case. That's true until we get right to that point of intersection, and then afterwards, notice the rectangle is between y equals 7 minus x and 0. So if you're using the vertical rectangle, you'd have to actually use two integrals to integrate this. So let's go ahead and see how that would work. So the first integral, region starts at x coordinate of 1, stops at x coordinate of 5, and this one would be square root of x minus 1 minus 0. Just square root of x minus 1 dx. That would give you the area up until the dotted yellow line there. But then we'd have to add integral from, this one's, the region starts at x coordinate of 5 and stops at the x coordinate of 7. So from 5 to 7, and then on this one it would be 7 minus x minus 0 times dx. So that's the setup using vertical rectangles. But now let's see what would happen if instead we decided to use a horizontal rectangle. Well, with a horizontal rectangle, notice no matter where I draw it, it's always between the same two curves. So the advantage there is you wouldn't have to split it into two separate integrals. So I'll just draw it right here, and then that'd be dy. What you would have to do, though, is to solve, to get these everything in terms of y, if you're using a horizontal rectangle, you have to solve these for x, which isn't too bad in this case. So to solve this one for x, you would just square both sides. Give you y squared equals, the squared and the squared cancel out, x minus 1. So solving this one for x, is you would x equals y squared plus 1. And then the other one, it's probably even easier. Solve that one for x, you can just add the x over, subtract the y, so you get 7 minus y. So to set up the integral using a horizontal rectangle with dy, it'd be the integral from now, though we're looking at the y coordinates. The region starts and stops. So you go from bottom to top here. So that you can see the region starts at a y coordinate of 0, right there and there. And the region stops at a y coordinate of 2. So the integral from 0 to 2. And then the way you decide which one goes first is the one further to the right, because that has the bigger x coordinate. So that one is the 7 minus y. And then minus the one further to the left is the y squared plus 1. You notice everything's in terms of y. So put in parentheses. And then the whole thing times dy. So that would give us the same answer as those two separate integrals using dx added up. So it says now choose one of these to evaluate to find the area of r. So you can do either one, but in this case it's probably going to be easier with the y's because it's only one integral, and notice we also get to substitute in 0. So let's work this one out. So if you simplify what's inside there, we'll get 7 minus 1 gives you 6, minus y, and it should be the negative minus y squared times 2y. Now let's go ahead and integrate that. So that would give you 6y minus y squared over 2 minus y cubed over 3. Evaluate it from 0 to 2. So if you plug in 2, you get 6 times 2, 12, minus 2 squared over 2, that's 4 over 2 is 2. And minus 2 cubed is 8 over 3, and then we substitute in 0, notice they're all 0. So that gives you 10, which is 30 thirds. minus 8 thirds is 22 thirds, and this is area, so it's units squared. Okay, let's take a look at part B of the same region enclosed. Part B says that region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis. So when you have these cross-section problems, you don't have a choice which way the rectangle goes here. And it says it's a semicircle. Okay? So let's go back at our graph here. Here's the x-axis. So perpendicular to that, here we'd have to use the vertical rectangle, which means we'd have to split it up into two separate ones, just with volume instead of area. So recall for a semicircle, on the notes, previous section of notes, remember we derived the formula for cross sections with a semicircle. The area was pi over 8 times the base squared. And so we just need to figure out our base. Well, oops. The base on this one is square root of x minus 1, and the base on this one is 7 minus x. So like your base 1 and your base 2. So when we set it up, we'll have pi over 8 on the outside, both of them. Integral from the first one from 1 to 5. But now it'll be the base square root of x minus 1 squared. Dx, that'll give us the volume up until that dotted yellow line. And again, if you want to cancel out the square, you can, but you don't have to. Plus, unless you're going to integrate it by hand, pi over 8. The next one is the integral from 5 to 7. And that base was 7 minus x, but now it's squared. And if we could work out each of these, it's not too bad to integrate. But it says write but do not evaluate an expression involving one or more integrals that gives the volume of a solid. So all we had to do was set it up, basically. We don't have to work it out. If you do work it out, it's not wrong, it's just not necessary. That's all it's asking for, just to set it up. All right, let's take a look at another example now. This one says, let R be the region in the first quadrant bounded by the graph of y equals 2 times the cube root of x. So that's this equation right here. The line x equals 8. The line right there. And the x-axis, right, as shown in the figure above. So we've got this region right here. Find the area of R. So here, I use a vertical rectangle. Yes, you can see we won't need to split it up. It's always between the same two curves. So let's go ahead and set up the integral there. The integral from, you can see the region starts here at 0 and stops at x coordinate 8, so 0 to 8. And the area would be function on the top of the rectangle to cube root of x, which is the same as x to the 1/3 minus the x-axis is just y equals 0. So if we integrate that, we get 2 x to the 4/3 divided by 4/3 is the same as multiplying by 3/4. Divided from 0 to 8. Pull out the constant there. 2 goes into 4 twice, so you get 3 halves on the outside. And then if we switch that to radical form, that would be the cube root of x to the 4th. So we got 3 halves. Put those in. Plug in 8, so that'd be the cube root of 8 to the fourth minus the cube root of 0 to the fourth. Cube root of 8 is 2. 2 to the fourth is 16. And then 2 goes into 16. 8 times 3 gives you area of 24. In this case, it's area, so units squared. So that's the area of the region. Pretty standard problem. Nothing complicated about that. But that leads to part B, which is a little bit different. It says now the vertical line x equals k divides R into two regions of equal area. Write an equation involving one or more integrals and use this equation to solve for k. Alright, so we have a vertical line x equals k. Let's change things up a little bit here. So let's see what that would look like. So let's go ahead and draw it in there. So we got some vertical line. I'll just guess about where it might be. Maybe about right there. X equals k. So that this area right here is the same as this area right here. So there's a couple different ways you can do this, but probably the easiest way, you could take either one of these regions. We know the whole area is 24, right? And set equal to half of that total area. So I'm going to use this one because we get to start at 0. It's a little easier. So we can go from integral from 0 to k of 2x to the 1/3 dx equals half of the whole area, which was 24. Or you could also go from k to 8. That would work as well. And you'd have to substitute 8 instead of 0. Or instead of equaling to half the area, you could also set integral from 0 to k equals the integral from k to 8. It's the same area, either way. But this is probably the easiest way to set it up. So notice we've already integrated this. And if you take a look at what we got here, before we plug things in, it was a 3/2 cube root of x to the fourth from 0 to 8. So if you want, you can skip right to that. We're going to get the same thing since we're integrating the same thing. Up to that point, cube root. So it was a 3/2 and then the cube root of x to the fourth. What's different though is now we're going from 0 to k instead of 0 to 8. And then a half of 24, 2 is a 24, 12 times. And now we're actually going to use this equation to solve for k. So on 3/2, you substitute in k there. It will be the cube root of k to the fourth minus, you plug in 0, which is 0, equals 12. And then to keep solving for k, if you want to get rid of the fractional one step, you can multiply by the reciprocal, 2/3. So we get the cube root of k to the fourth equals 12 times 2 is 24, divided by 3 is 8. Or you can go 3 goes into 12 4 times 2 is 8. And then take the fourth root of both sides. Get rid of that exponent of 4. Give us the cube root of k equals the fourth root of 8, which doesn't simplify really. And then to get rid of the cube root, you would cube both sides. So k would equal, nothing really we can do to simplify this, the fourth root of 8 cubed. Or you could say 8 to the 3/4 power, that's the same thing. So that's where we divide the region into two regions of equal area. Okay, let's take a look at another example now. This one says let R be the region enclosed by y equals x cubed minus 9x and y equals sine of 2 pi over 3 times x as shown to the right. So we've got the graphs right there. So let's go ahead and enter these in our calculator. This is a calculator problem. With calculator problem, I should say. So clear out these, and we'll have x to the third power minus 9x, and then sine 2 pi. Okay, when you're doing trig functions, make sure your calculator is using radians for the mode, not degrees. Pi. X is really on the numerator here. Then divided by 3. And let's look at our window size here. Looks like we're just in the first and second quadrants. So for window size, I'll set the x minimum negative 1. Let's try 5 here maybe. See if that works. And then y minimum looks like it needs to be pretty low there. Maybe negative 10. Y maximum, maybe 2. Let's see how that looks. So there's the first one. I could have made it a little lower. Okay, so that looks pretty good. We just can't see that. If you want to see a little better, you could make the y minimum maybe negative 12. There we go. Now we can see the entire x cubed graph. We need to see, and then there's our region enclosed right in there. The reason why the discrepancy here, why this one's so stretched out, this one is not to scale because it has different scales on the x and y axis, and this is what it really more looks like because this is the same scale on the x and the y axis. So we can label these. Might have been obvious when you're just looking at it, but the one on the top there, that's y equals sine 2 pi over 3x. And the one on the bottom here, is y equals x cubed minus 9x. Okay, so it says the horizontal line y equals negative 3 splits the region R into 2 parts. So let's go ahead and graph that here. Got a horizontal line right at negative 3. So roughly about right there. So it splits this into 2 parts. So we've got this region up here and then this region down here below. It says write but do not evaluate an integral expression for the area of the part R that's below this line. So we want to find the area below this line. So you can see, well, should we use a horizontal or vertical rectangle? Well, a horizontal rectangle wouldn't really work here because it's the same function here. And you'd have to solve this for x, this one for x, which you can't isolate the x. So it's impossible to use a horizontal rectangle here. But notice if you use a vertical, it's always between the same 2 curves here. So there's no need to use a horizontal one in this case. Oops. So let's go ahead and set this up. But what we do need our calculator to figure out now here are these 2 points of intersection. So I'll call those A and B. That's where the region starts, and that's where it stops. And those will be the x coordinates since we're using a horizontal rectangle, everything in terms of x. So let's go ahead and find those. In order to find those, you have to enter one more thing on our calculator, and that's the line negative 3. So I'll go ahead and do that. For y3, negative 3. So right like that. Alright, so to find those now we just go second calc, intersect. First curve is y1, it's x cubed minus 9x. enter, but second curve is not y2, so hit the down arrow and choose y3 for the second curve, -3. And then guess, I'll guess this one's over here at 0.2, and so A equals 0.33760896. So write it down on paper and then store it in your calculator so you don't have to type it in. And let's go ahead and find our other point of intersection. So second calc, number 5, intersect. First curve again is y1, it's our cubic graph. And second curve this time, oops, we don't want to choose y2, hit the down arrow and y3. Guess, I'm going to move the cursor over here. Guess about right there. So it's 2.8169141. That's B. And let's store that in our calculator as well. In this case, actually, we didn't have to store them because we're just writing but not evaluating. But normally you would if you had to work it out. So this integral, the area would be from A to B. We still needed to find where they were. And notice the function on top, it's a little weird, but it is -3. Minus the one on the bottom is the cubic graph here. X cubed minus 9x. And the whole thing times dx, so that would give us the area. And since again it just said write but do not evaluate an integral expression, the area of the part R that's below this line, that's it. We don't have to work it out, although we could work it out. Alright, let's take a look at the next example. Oh, I guess let me just show you on the Inspire real quick first. Pretty much the same thing on the Inspire here. We would type those equations in. We don't even need the sine one actually, although I'll type it in here so you can see how it works. So x cubed minus 9x and sine two pi x over 3 and -3. I'm going to change our window size. Make that -1 to, let's see, 4. I don't think we need it all the way to 5 there. And then y minimum, I think we made that -12. Y maximum 2. Okay, so there we go. And then again, to find your points of intersection, what you do here on the Inspire menu, analyze graph, intersection. So notice now, since we have 3 graphs in here, it says graph with a question mark. So you have to click on which 2 are intersected. So click on there, F1 and F3, and then do the lower and upper bound. So it knows which ones are you trying to find are intersected. And then you would store that. It's A, and same thing for your other point of intersection.
click on the two graphs that are intersecting there. Lower bound, upper bound, and there's our other point of intersection. Okay, now let's take a look at the next example here.
So this one says, let R be the region bounded by the line y equals 5. Here's y equals 5. And the graphs of y equals negative 2 natural log of x and y equals 6 arctangent of x minus 2 as shown in the graph above, and then find the area of R.
Okay, so again, this is a calculator with calculator problem. So let's go ahead and enter these in. Got 5. Oops. It's negative 2 natural log of x and 6 arctangent of x minus 2. And let's change our window size here from negative 1 to, let's try 5. Y minimum, let's make that negative 3. Y maximum, let's see, we've got y equals 5, so maybe 6. See if that shows it to us. There's the first one, second one, there's the third one. Okay, so that gives us a good view of that region.
And you can see it graphed it in the order that we typed them in. So graph the horizontal line y equals 5 first. Then the second one we put in was negative 2 natural log of x. So that's this one. And then the third one we put in was 6 arctangent of x minus 2. So that's this one. And to find the area of R, notice on this one, if we used a vertical rectangle, here's between 5 and this curve, but notice you have to split it right there, and then be between 5 and this curve. So you could do that. But here's where it's advantageous to use a horizontal rectangle with dy. Because notice with a horizontal rectangle, it always stays between the same two curves, no matter where you are then. So what we do now is, well, we have to find point of intersection, but since we're doing everything in terms of y, A here represents the y coordinate, or point of intersection. So the integral, well, let's find A first, using our calculator.
So second calc, number 5, intersect. First curve, don't choose y1. Down arrow, so it's negative 2 natural log of x is intersecting y2 with y3, 6 arctangent of x minus 2, and guess. But be careful here. What we're interested in this time for A is not the x coordinate like we usually are, but the y coordinate, since we're using a horizontal rectangle with everything with dy. So it would be negative 1.176994. And then to store this, it's a little bit more difficult when it's the y coordinate on the 84. You write it down on paper first, and then second quit, and then you actually would type it in. So negative 1.176, because it's not automatically stored as the answer like the x coordinate is. 994, and then store alpha A. All right, and the other thing we have to do on this one, in order to set this up, because the integral now would be from A, that y-coordinate where they intersect, to 5, where the region stops. We have to get these in terms of x, because we're subtracting this x-coordinate minus that x-coordinate. So we have to solve these both for x one at a time, so let's go ahead and do that. So let's say we start with the y equals -2 natural log of x. So to solve that one for x, first thing you do, divide by -2. So you have y over -2 equals the natural log of x, which remember is the same as log base e of x. And then to switch it to exponential form, remember that what you do is you'd say the base is e, and the exponent is -y over 2, that would equal x. But that one actually is going to go second because it's further to the left here. So the one that goes first is this one, the one further to the right, which we'll have to solve as well. So if we solve that one for x, we've got y equals 6 arctangent of x minus 2. So again, we'd have to divide by 6 first here. So it'd be y over 6 equals the arctangent of x minus 2. And then, to get that x outside of the arctangent, you'd have to take the tangent of both sides of the equation. So that'd be the tangent of y over 6. The reason why you do that is because the tangent and arctangent are inverse functions, so they cancel each other out. So when you take the tangent of arctangent, you're just left with what's inside it, x minus 2. And then you just add the 2 over, so you get x equals tangent y over 6 plus 2. And since that one's further to the right, that one would go first in our integral. So the tangent y over 6 plus 2, and then minus the one furthest to the left we found was e the -y over 2, all times dy. The integral we set up to find the area. And since those in that form are not put in our calculator, here's how we'd put it in our calculator. There's nothing on the outside, so it just would be math number 9, function integrate. And we'd have tangent. Now on the 84 calculators, or 83 or 82, one similar to it, whatever the variable is, you always use this x, t, theta, n button. So in this case, it happens to be y. We're just going to make it look all like x. So it'd be x. This is basically the variable button. Tangent x divided by 6, close parentheses, plus 2, and then minus second e to the negative, again, I'm just putting x over 2. Okay, so that's where we're integrating. And then comma, x is the, or in this case y is the variable, and then lower limit alpha a, upper limit 5. So we get 11.180 or 11.181. I'll just write out the whole thing there. 1807109. So you just have to be accurate to 3 decimal places. So you can either make it to 180 or round it up to 181. Or write the whole thing out like I did with it. Then part B says the horizontal line y equals k divides R into 2 regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. Alright, so we've got some horizontal line now.
It's dividing this into two regions of equal area, so I'll call this y equals k here. And so we know this area right here is the same as this area right up here. So you can either, two ways you can set this up. You can either go from A to K or from K to 5. It doesn't really matter. I'm just going to go from K to 5. But either way, they're the same. And then of the same integral we had here, so tangent y over 6 plus 2 minus e to the negative y over 2 times dy. And now we have to equal, this we're just setting up right, but not solving it, half of the area we got right there, which was 11.187,109. And that's all I have to do to set it up. It doesn't, this one you don't actually have to solve like we did the other way. Now let's quickly look at how you do this on the Inspire. So let's add the graphs first. So we'd have 5 and negative 2 natural log of x. In this case, on x, when we start entering the integral part in this part, we can actually use y. And then we've got 6. 6 arctangent x minus 2. Okay, and then let's go to menu. Let's go from negative 1 to 5, x min max, and negative 3 to 6 on the y-axis. Okay, so there's our region again. And again, to find that point of intersection, you would just go menu, analyze graph, intersection. Again, you have to click on the graph, so it'd be F2 and F3, lower bound, upper bound. And again, since the y-coordinate we're interested in, since we used a horizontal rectangle, you would just click on the y-coordinate this time and store as a so a little easier on the Inspire. And then to integrate this, document insert the calculator part. You would just have integral, definite integral, from a to 5 and then it was tangent. Here you can actually use y on the Inspire, so it looks more like what you wrote down on paper there, of y over 6 plus 2 minus e to the negative so y over 2, let me just double check here. Yeah, y over 2. And then dy. You can see we get the same answer on the Inspire. Alright, let's take a look at one more example. This one says determine the area enclosed by the curves y equals x cubed minus 9x squared plus 16x plus 7 and y equals e to the 0.23x. So let's go ahead and enter these in our calculator. And I'll do the 84 first. Clear those up.
And make sure you parentheses around the x there, and the 0.23, so that whole thing is in the exponent. Now if we graph it with our current window size, can't really see things very well, can we? So it looks like we need to make it much bigger here. Let's make it negative 10, 10. Let's kind of switch it to our standard window size, see if we can see it better that way. Negative 10 to 10, so determine the area enclosed by the curves. So there's the first one. There's the second one. So it looks like there could be a region here or a region here or both. So it looks like our x-min doesn't have to be this small, this big, but our y-min and max need to be bigger, and the x-max, we can reduce that a little bit. So let's change our window size. Let's make the x-minimum -1. We don't really need to see everything else over there. X-maximum, let's try 8. And these we need to see a little more of, so let's try -15 to 15. How about that? Yeah, so there's the first one. Now we can see it better. And there's the second one. So we can see, in fact, there are 2 different regions enclosed. So let's sketch that on the graph there. So when it says the area enclosed, it's referring to both of those, not just one of them. So I'll just do a rough sketch of these. So here's y equals e to the 0.23x, and this is y equals x cubed minus 9x squared plus 16x plus 7. So to see if it's better to use horizontal or vertical rectangles this time, start with a vertical, and you can see, well, vertical always stays between the same 2 curves, it's just there's 2 different regions there. So it's better than horizontal where you'd actually have to split it here. It's not always between the same 2 curves, and you'd have to do this curve minus itself, which is impossible to do since you can't solve for x. So the best choice here is definitely using dx with vertical rectangles. It's just because we've got 2 different regions, we'll have to split it up into 2 integrals as well. But within each of these separate regions, it stays between the same 2 curves. So what we need to find here are the x-coordinates of our points of intersection. I'll call those A, B, and C. So let's go ahead and do that using our calculator. So calc intersect, first curve was only 2, enter, second curve y2, enter. I'm going to guess the first one's at negative 0.2. Yeah, so it's negative 0.3198439. And let's store it in our calculator. It's A. Let's find our second point of intersection. And first curve enter, second curve enter. I'll guess this one's over here. It looks like around 3. So I have to move my right arrow way over there. And it's 2.91381159. Sorry, 1859. And let's store that in our calculator. B, and then one more. I'll guess this one's over here at 7, or I just typed in 8, I guess. So it's 6.4623727. quit and store as alpha c. Alright, then let's go ahead and set up our integrals here. There's only two of them now. The first one, the integral starts at a, stops at b, and you can see using this rectangle, the one on the top is the x cubed minus 9x squared plus 16x plus 7 minus the one on the bottom is e to the 0.23x. dx plus, that would use the area of the first region enclosed there, plus the next integral would be from starting at b, stopping at c, those x coordinates. This time, look at our rectangle, the function on the top is e to the 0.23x, the one on the bottom is the other one, so e to the 0.23x minus this whole thing, so x cubed minus 9x squared plus 16x plus 7, and all the times dx. And this one actually says determine the area, and I just set it up, so let's go ahead and use our calculator to work this out. Okay, so we can put this all in at once. So math, number 9, function integrate, and we've got this one is our y1 and this one's our y2, so variables, y variables. So we do y1 minus variables, y variables, y2, comma x, comma the lower limits alpha a, comma upper limit alpha b. Before I hit enter, I'm just going to put plus, so we can do this all once. Math, number 9, function integrate. This one, this time it's y2 first, minus y1. So variables, y variables, y2, minus variables, y1, comma x, comma lower limit is b, comma upper limit is c. We get 66.123 if you truncate, or 124 if you round it. And again, these are units cubed. Or you can write the whole thing out if you want. Okay, now let's just do the same thing with the inspire. If I do new document, add the graphs. Got x cubed minus 9x squared. Oops. There we go. Gotta finish that one up. There we go. And then second one is E. (0.23x). And again, change our window size here. Change the x minimum to -1. We've got 10, and then y minimum, we had it was negative 15 to 15, I think. There you go. So we can see the regions enclosed now. So now let's go ahead and find our points of intersection. New analyze graph intersection. There's the first one. Store is A. Second one. Store is B. The last one. Store as C. Okay, and then let's insert calculator. And the first one was the integral from A to B. And this one was the first one we typed in, f1 of x minus the second one we typed in, f2 of x dx. Whoops. And then plus, second integral was from B to C. And this one, the e to the 0.23x was first, so that was f2 of x minus f1 x dx. And you can see we get the same answer that way, 66.123, or if we round it to 124. And that concludes the notes for AP Calculus on the topic of advanced area and volume problems.